Okay, my name is Donovan Chipman. I'm a PhD student at the University of Utah. This is not anything to do with my dissertation or anything, it's just kind of a hobby. But I'm going to be talking today about retro propulsion technology in regards to landing large objects on Mars. So there's the overview of the presentation. I'm going to give an introduction and talk about EDL methods and talk about the solution and look at some simulations. So the largest mass that we can currently land on Mars is on the order of 1 ton, and we're going to need to be able to land between 10 and 100 tons to do anything resembling a realistic manned mission. Also, current probes suffer between 12 and 16 Gs on re-entry, and for people you don't want to be above 8 Gs, and you would prefer to be below 3. Methods that we use currently to get to Mars and to the surface are propulsive aero braking, or propulsive aero capture, in which you fire your rocket engine, get halfway down to orbit, and then you can aero brake the rest of the way. To get down to the surface, you can use a heat shield. It's a 70-degree sphere cone. It's been used since the 1970s. You can use parachutes. Once you get down to around Mach 2.2, 2.3, you can see some shock waves coming off of them there in the first picture. The second one's just another picture. Then once you're done with your parachute, you're down around 60 meters per second still. That's still too fast for regular landing, so you either have to fire rocket engines beneath you, use airbags and bounce along the ground, not good for people, or you can place the rocket engine above you, like with the sky crane on the most recent Mars mission. There are more advanced methods that we could use to help improve our fuel efficiency and other things. One of those is to use a deployable heat shield. These are a couple of items that NASA has been working on. One's an inflatable heat shield. Another one is a foldable heat shield. They both have their advantages and disadvantages. You might use something besides the 70-degree sphere cone. You might use a biconic heat shield. It has a better lift-to-drag ratio. That can help improve your payload. Another idea is to use nested heat shields, regular traditional ceramic-type heat shields, one for aero capture and one for entry. That prevents problems of cracking and other issues that have been discussed. But there is potentially a mass penalty for that. Another option that's currently being developed is to use some type of magneto-shell, magnetic field, to try and capture yourself into orbit. That's potentially much lighter than other options, but again, unproven. You could use more advanced supersonic parachutes. If you can get up to Mach 3 and have a 30-meter diameter heat shield, or 10-meter diameter heat shield, you could potentially land up to 30 tons. It's getting that Mach 3 deployment that's really hard. Another option is to use supersonic retro propulsion. This has never been tried or tested. It potentially has a lot of advantages, but you've got a rocket producing exhaust with shock waves in it, and you've got a vehicle flying through the atmosphere producing shock waves. Those shock waves interact, you get recirculation going around the vehicle, could cause overheating. There are a lot of issues with this. It's a good option if it works, but it still needs to be developed. Also, you could place the engines around the outside of the vehicle, and that would help reduce some of the interactions, some of the things being looked at. But in case none of this works, and I find it doubtful that it would all fail, but here's a fallback solution. You can try and fire a rocket engine in orbit until you get down to subsonic velocity before you hit the atmosphere and stay subsonic all the way down. For these simulations, I call them simulations, they're more like back of the envelope Excel spreadsheet type things, but they are time steps. So one-dimensional and two-dimensional flight paths. I consider one-stage and two-stage designs, nuclear and chemical, hydrogen and methane fuels. These are low-fidelity simulations. The time steps were between 0.05 and 5 seconds, depending on the simulation. All of them start with a mass of 121 tons. I only considered thrust and gravitational force. Because of the low velocity, drag should not be as much of an issue. Two-dimensional simulations account for the rotation of the planet. The one-dimensional simulations don't, so there's some introduction of error there. The two-stage vehicle is staged at interface with the atmosphere. All thrust is directed parallel to the path flight, unless, of course, you're within the atmosphere, and then it's a small angle off of the direction of flight. There are some other things defining the parameters. Thrust-to-weight ratios for engines, for nuclear engine, was defined to be 4.5. Propellant tank mass was 6. So now we get to the fun stuff. How do you get this how do you get 120 tons from low Earth orbit to Mars? Well, if you're using something like 1950s technology, like the Titan II first stage, you would need 3 SLS Saturn V type equivalent launch vehicles. If you're using cryogenic technology with liquid hydrogen and liquid oxygen, you'll need 2 SLS launches for a vehicle of this size. If you have nuclear, you can do it with 1 more SLS launch, and the same is true with state-of-the-art electric engines. And if you can get an electric engine with 10,000 seconds, you might be able to do it with an additional launch with something like the SpaceX Falcon Heavy, and you could possibly even get directly to low Mars orbit using that. So let's look at some of the simulations. With hydrogen and oxygen, specific impulse of 470 seconds. You can see the altitude versus velocity and altitude versus mass there. You see most of the mass and the velocity is bled off before you hit the atmosphere at 100 kilometers. And the results are your maximum g-force that is felt with this case is about 2.3 g's, and your payload is 12.4 g's. So what type of a mission can we do with this type of payload, with this landing mass? Here's one example. It's not really what the presentation is about, but it is a possible use. So let's say you have a 100-ton liquid hydrogen, liquid oxygen upper stage based on United Launch Alliance's advanced cryogenic propulsion systems. You launch one of them on a heavy lift launch vehicle, possibly with a tug like an automated transfer vehicle to provide power and propulsion. And do the same thing with the second one. You dock them together. You add on a third stage, and then on top is a landing vehicle. Don't get too much into the shape. It was an old design I just put in this morning because I made all these renderings today. You do the same thing for the crew habitat. You send up 3 stages and something like a large Bigelow habitat or a NASA International Space Station type design. And then you send up a crew on a smaller rocket to dock with it. At that point, they both take off in convoy. You see the Mars landing vehicle here. The habitat would go off with it. Once you get close to Mars, you take that capsule you launched in, you go and you dump all your stages, you go and dock with the landing vehicle, and then you do a direct entry while your habitat, with that third stage that's still there, propulsively brakes all the way into low Mars orbit. Your landing stage fires, you get taken down to the ground, you get out, you explore for a little while, you get back in, you fly back up. And then you use what's remaining in that third propulsion stage, you take yourselves back to Earth, and you re-enter and land. That's an option. So that's what you can do with direct entry using only liquid oxygen, liquid hydrogen propellants that we have available today. But let's say we can add some technologies. What if we find some way to aero capture? What if we have a nice ceramic heat shield or a nice magnetic field that we can use that doesn't weigh a large portion? So you start from low Mars orbit instead. Go back up here. All right. Here's some charts showing some of the output. I had to stay within a velocity box and radial versus tangential to make sure I never went supersonic while landing, because part of the importance of this is we stay subsonic. And at output, what we get is a maximum g-force of 1.94 g's, down from 2.3 g's previously. And then a payload nearly double what we had before, 25.5 tons. So with this much payload, we can do a mission that looks like this. So in 2 separate vehicles, you could land your habitat, you could land your Earth return vehicle. You might not even have to aerobrake the habitat into Mars orbit. You could just go get in your ascent vehicle and rendezvous with it. So for comparison's sake, what if you could develop supersonic retro propulsion technology? Same looking charts. Important thing, with direct entry, your payload is about 20 tons. It's not as good as from low Mars orbit, but it's only one technology that you can add. But what if we add supersonic retro propulsion and aero capture? Then how much payload can we land? Well, for some reason that chart didn't show the planet. That's kind of disappointing. Again, similar looking charts, no numbers. Okay. And so your payload, in this case, is now 42 tons. That's significantly larger. And then here on this chart, I'm just showing what if you use methane, what if you use nuclear. The two I showed are the two architectures that we considered earlier. But with nuclear, you can land potentially up to 73.3 tons with supersonic retro propulsion. Your maximum G-force would be only 0.65. Might not even require in-space conditioning. It's so low. So just some basic observations. Man, I flew through this. For chemical combinations, half or more of the total mass following staging is usable payload. So what this suggests to us is that the largest gains to be made are in the in-space propulsion units. Also, for nuclear vehicles, the total payload isn't much greater than chemical vehicles unless you count the mass of the nuclear rocket. And if you count that, because you can use it, then your payload increases greatly. You can use it for propellant production, for power, for ISRU. You can use it for ascent propulsion. You could theoretically extract carbon monoxide directly from the atmosphere, crack it from the CO2. And you could use the same hydrogen engines for ascent. So there are options to be used there. For future work, obviously we'd be talking about better modeling of the atmosphere, or modeling of the atmosphere at all, aside from treating it as a rotating body along with the planet. Greater ability at automatically varying thrusting forces and direction. The introduction of an optimization model. And simulations with more advanced software packages. So the conclusion in all of this is that subsonic retropropulsion is a good way to avoid the need to develop supersonic retropropulsion technology. Without other enabling technologies, such as low-cost launch prices, nuclear or electric propulsion, advanced aero capture methods, it is less practical, but perhaps not impractical. And with other enabling technologies, it is competitive with more traditional EDL methods. So for example, the Mars Science Laboratory was launched on an Atlas V rocket. The particular version of Atlas V rocket that was used was able to put 17.4 tons in low Earth orbit. The missions we considered would require 321 tons for one of those stacks. You are able to land using this fully retropropulsive technology 13.2 tons approximately, whereas if you use the current method, you could land about 16 tons. So you get around 70%, 70 to 80% of the total payload using this in one piece. You don't have to split it up into 16 smaller pieces like you do now. So it has that advantage. But again, other technologies that you could include, such as nuclear, supersonic retropropulsion, aero capture, these technologies will allow far greater payloads. So this is kind of just a last backup if everything else fails. I guess we've kind of covered the results. Are there any questions from anybody? Yeah, but, no, there's a change in thrust, but the constant, this was modeled this way. So it was modeled with constant thrust while you're in space. And starting up higher, you're actually going slower than you would be when you hit the atmosphere because you're approaching the planet at about 3.6 kilometers per second. And by the time you hit the atmosphere, you're going somewhere between 5.5 and 6 kilometers per second. But if you start up higher, maybe you're only going 4.5 or 5 kilometers per second. So you have more time to bleed off starting from less velocity. And then when you hit the atmosphere, you either stage for most of these simulations, and your second stage has a lower thrust, Or like with the nuclear simulations, you turn off some of the other engines and you still have a lower thrust level. Because your vehicle weighs less at atmospheric interface than it does when you start, so you don't need as much thrust to slow down quickly. But for the most part, yeah, it was modeled with 2 levels of constant thrust.
I understand, maybe I'm wrong, that you are kind of trading off the total equipment needed for atmospheric acceleration, and you're trading that off against decelerating already outside the atmosphere. Is that right? Because from the energy, of course, the atmosphere saves a lot of energy to be put into deceleration.
I wouldn't even call it a trade-off. It's not that efficient. It's the trade-off is in regards to technology development. I mean, if I say I want to get there as fast as I can, if we do a crash program like they did with the moon, and this would take, I mean, as we saw, it would take about 6 heavy lift launches. That's the total number of Saturn V's that were used to land people on the moon in the 60s and 70s. So even doing it this way, it isn't terribly efficient. It's just that you don't have to develop new things, or at least not as many new things. You would actually have to develop the ability to store hydrogen for long periods of time. There are people that are working on that, and there are things like the integrated vehicle fluid systems being produced for the Centaur upper stage, in which you integrate all of your vehicle systems. You can integrate thrust for station keeping and engine tank pressurization and power production. And you can do all of these things with just a tiny little engine. Oh, and also potentially even propellant transfer, because you're actually pumping with the engine. So sorry, where was I going with that? And so the issue is you can get down to about 0.1% a day of hydrogen boil off, and which is still significant over the course of a Mars mission. And so what I would suggest doing, from that perspective, is once you've got your first and second and third stages up there, you would actually launch another rocket with hydrogen. Doesn't weigh much. It is 1/7 of your total propellant load. And so if you do that, you can have another small rocket launch, be fully topped off, and then you wouldn't need to worry as much about hydrogen boil off. But that's the major technology that would need to be developed for something like this.